Okay guys, to start off with, I'd like us to draw out the full electronic structure of both fluorine and chlorine. If you're struggling with this, please use your notes to help you from last lesson. What I'd like you to think about once you've got those diagrams is how will these atoms become stable? Will they gain or will they lose electrons? Once you've done that, if you're really on the ball, you can predict the reactivity of these two elements. Which of these two elements will be the most reactive? Which will be the least? If you're really struggling, and I'll leave this up to the cover teacher to decide, on the next slide is a bit of help to help you with this. Right? So if you're really struggling, first of all, look back through your books. And secondly, at the discretion of the cover teacher, you can see the next slide, which will help you even further if you're struggling. I think this should take you about 3 minutes, guys. Best of luck. So if you're needing a bit more help with this, fluorine is in period 2. That means that it has 2 shells. It's in group 7, which means that there are 7 electrons in the outer shell, and it has 9 electrons in total. On the other hand, chlorine is in period 3. That means that it has 3 shells. It is also in group 7, like fluorine, and it has 17 electrons in total. Please pause the video now and use what's on the screen to help you to complete the full electron configurations for fluorine and for chlorine. In terms of the answers then, fluorine has 9 electrons. There are 2 in the first shell, indicated by the black circles, although you may have drawn them as crosses. And there are 7 electrons in its outermost shell. 7 electrons shown here in blue. Of course, you might have drawn them also as crosses. 2 add 7 makes 9 electrons in total. In terms of chlorine on the right hand side, chlorine has 17 electrons. There are 2 in the first shell and then 8 in the next shell, shown by the black circles. Again, you may have drawn them as crosses. And in the outermost shell, it has 7 electrons, shown here by the blue circles. Again, you might have drawn them as crosses. 2 add 8 makes 10, add 7 makes 17 electrons. If you haven't as yet made a prediction about the reactivity of these elements, here's a clue for you to help you. Both of these atoms want to get an extra electron. They want to gain 1 electron. If they can gain 1 electron, they both will have a full outer shell. They both will have a full outer shell if they gain 1 electron. The question is, which atom will be able to gain an electron most easily? Will it be fluorine or will it be chlorine? I'd like you to write down your predictions now if you haven't already done so. The title for today then is Group 7. Group 7, the halogens to be specific. And what we're looking at today is what are the properties of the halogens and how can I show how their reactivity relates to electronic structure. I'm going to go through this. We don't need to write everything down apart from if I ask you to pause the video, but I'm going to tell you to write down the absolute key things from these slides. Group 7 on the periodic table is on the far right of the periodic table, and these elements, fluorine, chlorine, bromine, iodine and astatine, are called the halogens. The word halogen means salt former because, as we'll see when we come on to ionic bonding, these guys react very readily with metals and form salts. As we've seen from the start of this video lesson, all halogens have 7 electrons on their outer shell. This means that they can easily get a full outer shell by gaining 1 electron. When they gain 1 electron, they form negative ions with a -1 charge. They all have very similar chemical properties. What I'd like you to do is just to pause the video and just to write down those 3 bullet points which are on the screen. Once you've done that, we'll continue. So what are the properties of the halogens? Well, in general, all halogens are non-metals, and so as a result they don't conduct electricity. They're brittle and crumbly when solid. They're also tremendously poisonous and smelly. They become much darker as you go down the group. So fluorine is pale yellow, chlorine is yellow-green, bromine is reddish-brown and orange, and iodine is blue-black and purple. Again, can you pause the video just to make a note of those key things? I think it should take you no longer than a minute or 2. In terms of their states at room temperature, chlorine is a pale yellow, greenish yellow gas. Bromine is a brown liquid, and iodine is that blue-black solid. I don't have a picture here, unfortunately, of fluorine, but fluorine is a pale yellow gas. And astatine, if you could view it, well, let's have a think about what astatine might look like. Because from this information, fluorine being a gas, chlorine being a gas, bromine being a liquid, iodine being a solid, what do you think astatine will be in terms of its state? And here's a little thing to help you. What happens to the melting point and boiling point as you go down group 7? Why is that? And I'd like you to predict what colour and physical state astatine, the next halogen at the bottom of group 7, will be in at room temperature. Pause the video now, have a brief discussion, and then when you're ready we'll play and we'll go through the answer. Hopefully what you discussed is the fact that the melting point and boiling point increases as you go down the group. So fluorine is a gas, chlorine is a gas, bromine is a liquid, iodine is a solid. Astatine, therefore, you would predict would also be a solid. And the colour gets darker as you go down the group. So iodine being a blue-black solid probably means that astatine will be dark grey or even black in terms of its colour at room temperature. The boiling point and melting point increases as you go down the group because the extent of the intermolecular forces increases as you go down the group with more electrons at play. Okay, we're going to move on to the reactivity of the halogens. We've talked about their properties, but now we're going to think about how they react. And we're going to think about their reactivity in terms of displacement reactions. Now, I'm afraid I'm going to show my age, because when I was your age, the hottest couple at the time on the far left-hand side here was Brad Pitt and Jennifer Aniston. They were otherwise known as Brennifer. This, by the way, is supposed to represent a compound. Brad Pitt and Jennifer Aniston are married. They are a compound. Along comes Angelina Jolie, the lady in just to the immediate left of the arrow. And Angelina Jolie is way more reactive than poor old Jennifer Aniston. So what happens is that Angelina Jolie kicks out poor Jennifer Aniston, and there she is. Jennifer Aniston's looking really upset, on the far right hand side of this slide, and we have a new compound formed. We have Brangelina, Brad Pitt and Angelina Jolie. This is an example of a displacement reaction. How can we describe this in words? Well, a displacement reaction is where a more reactive halogen will displace a less reactive halogen from an aqueous solution of its salt. What does that mean? Well, aqueous means that it is dissolved in water, and displace means to swap out. Please, can you pause the video? Can you make sure that in your notes you write out that important definition in the red box into your notes? Okay, now that we know what a displacement reaction is, where a more reactive halogen will replace a less reactive halogen to form a new salt, and the less reactive halogen is kicked out, at this point we would usually do a experiment, a nice little practical. Unfortunately, obviously we can't, because A, it's a cover lesson, but B, we're not allowed up into the laboratory at the moment. If you were to do this experiment though, bromine water, chlorine water and iodine water, that is the associated halogens dissolved in water, are incredibly hazardous. They are, as we've talked about, they're toxic, they're poisonous, they're smelly. You would not want to get these into your eyes in any way, shape or form. Usually you would wear gloves when using them, and you'd also wear eye protection. Chlorine dissolves in water, and you've got experience of this because you've been to the swimming baths. And at the swimming baths, when you open your eyes sting because there is chlorine in the water. You have a very weak concentration of chlorine in the water. It's like chlorine water. It's there to kill bacteria and other pathogens to make it safe for everybody to use. So imagine getting bromine, chlorine or iodine water in your eyes, which are far more concentrated. It won't be simply that your eyes will sting, it will be that you would do serious damage to your eyes. So it's very important to protect your eyes using appropriate eye protection. Okay, you should have the sheet in front of you. If not, the cover teacher can pause the lesson and hand this out to you. What we're going to do is we're going to look at this experiment. We're going to look at another YouTube video, and you're going to log the results in this table. This table is laid out exactly as the practical will be on the screen. So down the left-hand side, you have a halogen solution, either chlorine, bromine or iodine water. And along the top, you have the halide solution. So these are salts which are dissolved in water. They're aqueous salts. You've got potassium chloride, potassium bromide and potassium iodide. You might be looking at this and thinking, why are there boxes which are greyed out? The boxes are greyed out because chlorine water isn't going to displace, isn't going to swap out for chloride within potassium chloride because they're the same halogen. Equally, bromine isn't going to displace bromide from potassium bromide, and iodine isn't going to displace potassium iodide from potassium iodide, which is why those boxes are greyed out. However, the positions of those are useful because they will act as a control. We're looking for changes. We're looking for changes in colour. And anywhere where we see a colour change, you can write out what the colour change is. It goes, for instance, from yellow to brown or what have you. That indicates that there's been a reaction. Where there is no reaction, we can write no change or no reaction. Hopefully it's clear about what you're doing. We're going to watch the video. As we're watching the video, I'd like you to write down any changes that you see, or indeed if you don't, you simply write down no change. And I will go through the answers shortly. So here is the video. Here's the video, guys. Here we go.
Here we are with a series of halogen halide ion displacement reactions. In the first three conical flasks here, we have potassium chloride. In the second three conical flask, we have potassium bromide. And in the third set of three conical flasks, we have potassium iodide. Into each of them, we're going to sequentially put iodine in this row, bromine water into this row, and chlorine water into this row. So let's have a look if any displacement reactions occur. Here's the iodine. You can see it stain the bottle deep brown colour. We're familiar with iodine. And if we place an approximate equal amount, a few mils, into each of those solutions, we see not much difference in the three. Same colour for the iodine, and nothing appears to have happened. Into the second sequence of flasks, we're going to put bromine water. So this is quite nasty stuff. And there's the bromine water. Quickly put the top back on the bottle. The bromine water, 0.02 molar. And let's introduce that into the three flasks. So we've got into the first flask, which is in bromine water in potassium chloride. This is bromine water into potassium bromide. And finally, bromine water into potassium iodide. And hopefully you can see there that the bromine into potassium iodide has turned a much deeper orange colour than the other two, perhaps indicating a difference in the reaction. Finally, we have chlorine water. Here's the chlorine water, and we're going to introduce that into the three flasks. So first, let's put some chlorine water into the potassium chloride. Then chlorine water into potassium bromide. And finally, chlorine water into potassium iodide. So once again, you can see a difference in the intensity of the colours there. The chlorine into potassium chloride, no noticeable change, but both into the chlorine into the potassium bromide, we've got a development of an orange-yellow colour, and into the potassium iodide, we've got that familiar iodine colour present there. So
there we are. So hopefully what you've obtained is something that looks like this. I will let the cover teacher pause the video so that you can jot this down, but after that we're going to have a go at looking at which is the most reactive halogen and which is the least reactive halogen. So if once you've got this down, you can have a think about which is the most reactive of these three, whether it's chlorine, bromine or iodine, which is the second most, and which is the least reactive. Pause the video now to have a think about that. Hopefully what you've identified is that chlorine water, and chlorine by extension, is the most reactive halogen, because it's reacted with both bromine, or bromide I should say, and iodide. A displacement reaction occurs in both cases. Bromine water is the second most reactive because it reacts with potassium iodide but not potassium chloride. There is a colour change. And iodine water is the least reactive, by extension iodine is, because it doesn't react with potassium chloride or potassium bromide. Okay, on this next slide, I have written out the four reactions which take place, which we've observed from the video. The first one I have done for you, which is chlorine plus potassium bromide makes potassium chloride plus bromine. I'd like you to have a go at the next two. This first one, just think about this in terms of the analogy that we made before, in terms of displacement reactions, with Angelina Jolie displacing poor old Jennifer Aniston. So you have a more reactive halogen displacing, swapping out for a less reactive halogen to make a new compound, and the less reactive halogen is kicked out on its own. Give you a few minutes to do this, guys. Please pause the video to do this. Okay guys, here are the answers. The first one of course was done for you. The second one, chlorine reacts with potassium iodide to form potassium chloride and iodine. And the fourth one, which I know is the third one, but it's the fourth one in your table, these are experiments 1, 2 and 4 from your table, is bromine plus potassium iodide makes potassium bromide plus iodine. If you're really up for having a look into this further in terms of the reactions and the chemistry here, what I've written out here are the equivalent balanced symbol equations. So this is chlorine water. The AQ on screen means aqueous. That means it is dissolved in water. That is a state symbol. Can you pause the video, guys, and have a go at writing these out underneath where you've written your word equations? Okay, so final slide and last little thing from me is the halogen displacement reactions. What is the trend in reactivity? What's the link to electronic structure? First and foremost, was your prediction correct? At the start of the lesson, you should have said that fluorine was more reactive than chlorine because fluorine is at the top of group 7. So equally, chlorine is more reactive than bromine, and bromine is more reactive than iodine, and so on. What we're going to do next lesson is look at what does the electronic structure, the fact that those electrons, the atoms are growing in size and the electrons are getting further away from the nucleus as you go down group 7, have to do with this reactivity. I'll give you a hint. It's got something to do with the fact that it's how easy it is to gain one electron to get a full outer shell. You could have a go at writing that out in your books. If not, what I would like you to do is to just simply write down 3 key things that you've learnt in today's lesson. And even if after you've done that and have finished everything, you could be having a go at some questions from the textbook. Thank you for your attention. If there are any problems, please don't hesitate to contact me through Teams. I'll see you soon, guys.